Picture an active assembly line. A 6-axis heavy industrial arm is executing a complex welding trajectory when, without warning, the system grinds to a halt. This freeze isn't a mechanical failure, it is a mandatory pause for programming. In legacy manufacturing environments, teaching a robot a new task or refining an existing one requires an engineer to physically manipulate the machine on the factory floor. While the engineer is coding, the machine is not producing. This creates an immediate industrial paradox. The core objective of optimizing a manufacturing process is to increase throughput and efficiency. Yet, to achieve that optimization, plant managers are forced to halt the exact production line they are trying to improve. The solution to this bottleneck lies in abstracting the control layer away from the physical hardware. We call this physical-digital decoupling. By separating the logic of the robot from the actual steel and servos, engineers can manipulate the code without touching the machine. To execute this separation, the physical arm is replaced by a mathematically perfect digital twin, mirroring the real-world counterpart's exact constraints. Platforms like RoboDK serve as the central environment for this decoupling, making the digital twin the primary target for all programming, simulation, and testing. Because the code is being directed at the virtual model, the physical arm on the floor is left completely uninterrupted. It continues running its current production batch at maximum capacity, while engineers write, test, and iterate the next program sequence entirely in the virtual space. Welcome to the Insight Engine. Today, we are decoupling the factory floor. The systemic breakdown and data architecture for this episode were provided by our analytical partners at Royal Research. Through their data, it becomes clear that true industrial agility is no longer constrained by the payload or speed of physical hardware. Instead, efficiency is determined almost entirely by the depth of a facility's software abstraction. This diagram illustrates the 3-pillar architecture of modern robotics: simulation, offline programming, and hardware integration. The workflow starts in the first pillar. This simulation space provides a mathematically rigorous, zero-risk testing ground where robotic interactions are mapped long before any physical steel is deployed. When testing complex multi-robot operations on an actual factory floor, the economic stakes are severe. A single miscalculation in joint velocity can result in a high-speed collision, leading to destroyed equipment, wasted materials, and days of offline repair time. On an actual factory floor, a miscalculation causing a collision destroys equipment. But in the digital twin environment, a mechanical conflict carries zero penalty. When virtual arms collide, they turn red. The software flags the error, and the environment instantly resets. This instant reset capability enables a high-speed parameter optimization loop. Because failure is free, engineers are encouraged to push the robotic system to its absolute operational limits to find the most efficient pathing. Programmers can isolate and adjust individual variables, tweaking a joint speed, modifying the approach angle, or recalculating payload limits based on different tool weights. Each micro-adjustment brings the system closer to maximum mathematical efficiency. Running thousands of these micro-iterations in physical space would take months of dedicated downtime. In virtual space, the feedback is near instantaneous. The system calculates the physical limits and provides visual confirmation of the optimized path in seconds. By testing entirely in software, the cost of engineering failure is shifted away from expensive physical capital. Errors are absorbed by infinitely renewable compute cycles, protecting the real-world balance sheet. This continuous digital testing environment naturally leads to the second pillar of the architecture, offline programming, or OLP. OLP is the execution and refinement of robotic code entirely outside the physical production facility. For decades, the industry standard relied on a device called a teach pendant. A human operator stands next to the machine, manually jogging the robot arm, recording coordinates one physical step at a time. There is a direct, unavoidable mathematical correlation between teach pendant programming and lost revenue. Every minute the operator spends holding that device, the machine is stationary, halting the production line and racking up downtime costs. This Gantt chart compares timelines. Top row, the legacy model, where programming and production are sequential. The bottom row reveals OLP's parallel architecture. As a vertical cursor advances, the physical production line in the offline model runs continuously at 100% capacity, introducing zero downtime. While real robots build today's product, engineers digitally code entirely new tasks. Both streams operate simultaneously. This parallel structure unlocks massive scalability. Within RoboDK, a single engineer isn't tethered to one machine. They can distribute programs to multiple robotic cells simultaneously. Because the OLK engine mathematically maps the entire workspace beforehand, every clearance, reach limit, and singular point is verified. The code generated is mathematically precise, guaranteeing that when the program is finally uploaded to the hardware, the first physical run is accurate. The act of writing robotic code is no longer a localized event that stops the factory. It operates as a parallel continuous workflow, functioning independently of the physical machines it controls. However, executing this workflow across an entire factory floor exposes a severe structural issue in the robotics industry: fragmentation. Historically, every major manufacturer has forced its robots to run on proprietary programming languages. This fragmentation is not an accident. It is designed to cause single vendor lock-in. If a robot cannot read code meant for another system, plant managers are pressured to buy hardware from only one manufacturer to keep production coherent. Hardware-agnostic platforms neutralize lock-in. RoboDK operates as a universal master compiler. Engineers write a single stream of generic logic. The central node translates that input into exact proprietary protocols for specific machines. This compatibility covers over 500 models, unifying a fragmented hardware market. This agnosticism breaks the dependency on any single hardware supplier. Factories can now deploy a cohesive workflow, directing tasks to a mixed fleet of robots from different brands, all controlled from the exact same interface. The software layer is further reinforced by its extensibility. The platform is designed to accept custom Python scripts and third-party plugins directly into the workflow. This extensibility means the system does not remain static. As industries evolve and complex new manufacturing parameters arise, engineers can write specific scripts to adapt the software to highly specialized, non-standard requirements instantly. By stripping away proprietary software constraints, hardware agnosticism effectively commoditizes the physical robotic arm. The unified software layer becomes the true center of value and control in the modern factory. Synthesizing this architecture reveals a clear, predictable workflow from initial design to physical execution, applicable across any manufacturing sector. The process begins outside the robot entirely. Engineers import 3D CAD models of the specific parts, tools, and the factory environment itself directly into the virtual simulation space, building the digital twin. Next, the offline programming engine calculates the required trajectories. It mathematically refines the robot's joints, verifies all physical constraints, and guarantees collision-free paths within that exact spatial geometry. Finally, a post-processor compiles this optimized logic and pushes the final code directly to the physical hardware on the floor, deploying the new task with zero interruption to the preceding workflow. We can map this exact sequence directly to the automotive industry. Scalable, continuous welding routines are programmed offline to ensure millimeter precision, then pushed to the assembly line without halting the flow of the chassis down the conveyor. In the aerospace sector, where tolerances are measured in microns, ultra-precise machining geometries are digitally verified against strict CAD models long before a single physical cut is ever made into expensive titanium stock. This identical logic applies to the high-speed sorting requirements of food and beverage packaging, or the meticulous assembly of consumer electronics. In every instance, the speed and accuracy of the output are guaranteed by the prior digital simulation. The future of industrial automation relies on a shift in perspective. To maximize efficiency, manufacturers must begin treating physical robotic hardware merely as a peripheral output device, no different than a printer receiving a document. The true factory floor is now purely digital. Abstraction platforms like RoboDK are the operating systems driving this architecture, allowing continuous, optimized global manufacturing. Thank you for watching. Special thanks to Royal Research for providing the data synthesis and industry analysis that made this episode possible.